So it's going to be alpha, k bar alpha minus 1, n bar 1 minus alpha, plus 1 minus delta. And then the same game, expectation time t minus the deviation from the steady state. Okay. So.
Why is the 1 plus 1 minus delta still there? If we take the derivative of 8 plus 1?
There shouldn't be. I was looking at that on the derivative. Thank you. That's very important. Thank you. I was looking at the above derivative. And now the same game with, let's do kt plus 1. So it's going to be, again, alpha, a bar stays the same. And then the exponent needs to go down of k, or kt plus 1. So it's going to be here. The exponent needs to go down, and I need to reduce it by 1. Okay, it's just a normal derivative. Okay, and now it's just nt left. And it's going to be 1 minus alpha times alpha a bar this is the same, and then expectation of nt plus 1 minus deviation from the system. Okay? So from here on, whatever we do is just algebra. Okay? This is all you have to do with the Taylor approximation. The rest is just algebra to get it to the form that we would like it to be, namely in deviations from the steady state. Those little hats. Because right now I don't have the little hats. In order to have the hats, I would have to have something like this here. Then this would be the expectation of the deviation from the steady state. Okay? Yeah?
I think there's two typos. So first of all, beta times 1 over c should be 1 over c bar, right?
Yeah.
And then there's n bar to the power of alpha, but it should be minus alpha, right?
Thank you. Okay. So the first trick we will do is notice here that this is the deviation, this is the steady state of 1 over c bar. Okay? Because in the steady state, the Euler equation is written as 1 over c bar is equal to beta 1 over c bar so it's written like this. So this term here is the right hand side of this. Okay? So I can just replace it with this so that it looks easier. Okay? Circle with 1 over c bar. rewriting this whole thing. I'm not doing anything else, okay? I just replaced that first term. Okay. So now, in order to get deviations from the steady state, so these little hats, what was the trick we did last time? Does anyone remember? When we had terms like this one. What did we do to get the deviations from the steady state? So we multiplied and divided by the variable in the steady state, so the steady state ratio. So, for example, this would be n bar over n bar. And I can do that because I'm dividing and multiplying by the same number, so I'm not essentially changing anything. But this will allow me to get these deviations from the steady state, these little hats, because that's the definition of them. Okay? So, we will do this for all the variables. In general, you should do this for all the variables. But in this case, if you see the term for Ct plus 1, it already has a C bar squared. So I can just break that up and use it to define my find my definition for the deviation from the steady state. I don't have to do this multiplication. It's just algebra. Okay? Let me show you. Let's test the variables. Except for Ct plus 1. Okay? That side we don't touch. This we don't touch because it's just a steady state. This I said we also don't touch, but I will write it like this. I will just split that 1 over c squared bar into 1 over c times 1 over c bar. Okay? And you will see why. I don't touch this bracket. I will just use the other 1 over c bar here, because this here will be the definition, so the Ct plus 1 hat. Okay? But I didn't touch anything there. I didn't do any multiplications. I just broke this fraction apart. Okay? For the rest, I have to multiply and divide. So. Of the deviation from the steady state for the hat. same for later. Okay? Now I will apply the definition of the steady state like I did for alpha for all of them. And I will just multiply, for example, there's a k there. There's an n bar there. I will just multiply it with this n bar here. So I'll just collect like terms. I'll just simplify them algebraically. Okay? Here there's no simplifications for now besides using the definition of deviation from the steady state. Here I will use this definition here. So what will remain is this times alpha bar, and I will just put it here so it looks like the production function. Okay? Because we will use it in a bit. Here I will multiply k bar with k bar alpha minus 2. So it will be k bar alpha minus 1. And there I will multiply n bar to the power minus alpha with n, so it will be n bar to the power of 1 minus alpha. Okay? From the definition of the steady state, notice that this part in the Euler equation, what is that part we said before? Yep.
The steady state.
Which is equal to? So this is the so this is this part of the steady state, okay? And it's equal to this. We can just put this in so that it looks a bit nicer. Okay? This is equal to 1 over c bar. And then the next simplification that we can do is these terms here. Okay? These are all equal to y bar over k bar. bar minus 1 minus alpha. Divide by k bar. Okay? So, I will rewrite this using all the simplifications we did. And
Sorry, but how are those expressions all the same? Isn't there like k bar to the power of alpha minus 2 in the second row? And then how can this be the same?
and this is, yeah, but remember I said I will multiply k bar, the top k bar of the fraction, with the k bar inside. So it's k bar alpha minus 2 times k bar, so it becomes alpha minus 1. Okay?
So the minus 1 from the derivative is always compensated for by the multiplied.
Sorry?
So we take the derivative for each variable, k and n,
Yeah.
but at the same time, like the minus 1, which like adds up to the, which we include by taking the derivative, is compensated for by the multiplicative of like n over n and k over k.
Yeah, so basically if you simplify this algebraically, you come to that expression at this step. But you're right, the derivative is that. You're right, these are the derivatives here. But then I multiplied them with whatever is left from that side, from the red part. Because this was the trick that we did, the algebraic trick, in order to get the definition of the deviation from the steady state. Let me finish it, and if you don't get it, we can talk about it. And what do we see now? Thankfully, that in a lot of the cases, we can take this as a common factor. Sorry, this part as a common factor. Okay? This y over k bar, it appears everywhere. Beta times 1 over c bar also appears everywhere, so I can pull it out as a common factor and have a more compact expression. I'm running out of time, so should we finish this or should we finish it next time? Because anyway, I don't think anyone's following that much right now. If you want, you can have a look at home. No?
No.
Who is for next time? Hands up. There, okay, I'm sorry. Have a look. Also, please have a look at the previous problems, because I think the most important part is understanding the derivatives, because otherwise it's just algebra. And we will finish this Okay, let's go to the second exercise. That is Excel. I will go